All right. Last week, guys. So the plan is today we're going to cover sort of this is going to be the last of the new material. We're going to talk about sections 13 point. Well, we already did part of 13.1, 13.1, and then kind of a select few important cases from 13.2 and 13.3. So quick little refresher. Remember last time we wrapped up by talking about this thing called a view factor. And the view factor was defined as, right, f I to j is the radiation heat transfer from a surface I to j divided by the total radiated power from surface I. So it's the fraction of the radiation leaving a body that hits another body. Okay, so we call this the view factor, and we introduced a couple of the first two of a set of 4 rules that govern these view factors. So with those 4 rules and just some insight, little mini example here. Let's suppose we've got this triangular enclosure. Okay, so surfaces 1, 2, and 3. We're given that the surface area of 1 is double that of 2. And we're given 2 view factors, F11 and F12. That is the fraction of radiated power from surface 1 that hits itself is 0. And the fraction of radiated power from 1 to 2 is about 30%. And from this, can we find F13 and F21? So this is going to require us to use the 2 rules that we talked about last time. If we wanted to find F13, anyone remember what rule for view factors would apply in that case? What it's called? So I'm hearing some whisperings with both of them. The 2 rules were the reciprocity rule and the summation rule. All right. And so in words, right, reciprocity rule says that if you know the surface areas of these 2 surfaces and you know the view factor of one of them, you can find the view factor of the other one. All right. The summation rule says that, like, if you sum the view factors from one surface to all of the others in an enclosure, they must equal 1. Okay. So this first bullet point here, we're looking for F13. The idea is from surface 1, if we know that 0% of its radiated power hits itself and 30% of its radiated power hits surface 2, then the rest of that radiated power has nowhere to go but to surface 3. Okay. So if F11 plus F12 plus F13 equals 1, then that means F13 has to equal 0.7. Right, so we'd find this one using the summation rule, which says that let's sum over j, actually. J equals 1, j equals 1. Okay. So in this case, that says that F11 plus F12 plus F13 has to equal 1. Therefore, F13 has to equal 1 minus 0.3 equals 0.7. F21. Okay, so if we use the summation rule for the first one, the second one, we're going to try out the reciprocity rule. Let's see how that comes into play. So remember, the reciprocity rule was written as follows. Reciprocity rule says that A1 F12 is equal to A2 F21. Okay? I'll let you guys chew on that for a few seconds. Um, Okay, anyone have a value for F21? 0.6. It is 0.6. So, all right, the idea here is if we're looking for F21, we're simply going to say we're going to divide over the A2, end up with that, right? And it's this relationship right here. This A1 is equal to 2A2. So this becomes 2. That's 0.3. So 2 times 0.3 equals 0.6. So view factors, right? This is basically the way view factors work. It's a lot of really easy math. It's just kind of puzzling out what numbers you can get from what you're given. And my shoe's untied for a moment. So in addition, that covers the two rules that we introduced in the last lecture, right? So those were, all right, the summation rule and the reciprocity rule. In addition to those, we've got two more rules that are kind of follow from these. They're not as commonly used, but it's worth stating them. The third is what we call the additive rule. Well, actually, before I get into the additive rule, I want to address one thing in this example. So here you were given, right, F11 equals 0. Okay. But in general, there's sort of a question of what is a surface's view factor with itself? Like, what does that actually represent? There are a couple of rules of thumb here. I'm going to move these down out of the way. So what is, right, FII, or, right, a surface vector with itself? So the idea, remember, view factor is how much energy leaving in sort of these radiated rays, okay, intersects another surface. What portion of that? So if we were to draw a flat surface or a convex surface, okay, the idea here is a point on one of these surfaces doesn't see any other point on the surface, technically. In this case, it's questionable because you're kind of at that limiting range, but remember that the projected area at a 90-degree angle is 0. And so for a flat or convex surface, the idea is that energy leaving the surface does not impinge back on that same surface. So for flat or convex surfaces, Fii is equal to 0, where in either case, right, this would be surface I. So that's why in this example we just did, right, that lower surface 1, we're able to say F11 is equal to 0. Okay, it's because it was a flat planar surface. However, if you have a concave surface, here, a point that's radiating energy, right? Some of that energy is going to come back and actually hit the same surface. And so for concave bodies or surfaces, Fii is not equal to 0. So the kind of the mnemonic here is like if the surface can quote unquote see itself, then you'll have a non-zero view factor, which kind of jives with the idea of what a view factor, or the name of a view factor. So in this case, the surface can't see itself, it can see itself. And so if radiated energy travels in the sort of line of sight, then that means that some of its own radiated energy will come back and hit it. All right, so with that out of the way, let's resume. So in addition to the summation rule and the reciprocity rule, I said that there's this one called the additive rule. And the additive rule is very it's very intuitive. Let's say we have a surface that's broken up into pieces. Okay, so it's a subdivided surface. And we're radiating energy toward it from some other surface up here. Okay, so this thing is, we'll call this surface A. So the additive rule says that F A, and we'll call collectively surfaces 1, 2, and 3. We'll call those B. Okay, so B includes 1, 2, and 3. So from F A to B is going to be equal to FA1 plus FA2 plus FA3. Okay, so this sort of is similar to the summation rule, but basically what it's saying is that the total view factor on a surface is a sum of the view factors on its parts. Okay. So for example here, if FA1 was equal to 0.1, if FA2 was equal to 0.25, and FA3 was equal to 0.2, right? The idea is then that this view factor from A to B would be equal to the sum of these three numbers. We end up with 0.55. Okay. So unlike the summation rule, this doesn't say anything about it summing to 1. It just says that if you split the surface up into pieces, those pieces sum together. Okay, and number 4 is the symmetry rule, which states essentially that physical symmetry implies radiation symmetry. And what I mean by that is if you have, let's say you have a make this larger. Okay, So let's say you have an enclosure like this. We'll say we've got surfaces 1, 2, and 3. And the whole triangular thing is symmetric about this line here. What this means is that if you know F12, it should be equal to F13 if 2 and 3 are symmetric with respect to the surface normal of 1. Okay, so this definition is more confusing than just the looking at it component. So let's say, okay, so another little comprehension check. Do we have enough information at this point between our collective rules that we would be able to say exactly what F12 and F13 are? So what is the value of F12? And it's going to take the symmetry rule and the summation rule to figure this out. I'm hearing a 0.5. That's right. Right. So we could deduce this from, first we could say from the summation rule. We have F11 plus F12 plus F13 is equal to 1, right? Surface 1 here is a flat planar surface, which means that F11 goes to 0. And then we have the symmetry rule, which says that F12 is equal to F13. And so from these two equations covering F12 and F13, right, the only solution we can get is that F12 and F13 are both equal to 0.5. Okay? So again, simple but sort of logical steps that you need to take in order to deduce the view factors. Okay, so we're going to shift away from the definitions a little bit and start talking about how we would actually use view factors in heat transfer problems. So to reiterate, this idea of a view factor, I want to reiterate 2 points. View factors assume diffuse radiation, okay, and second, the definition, the mathematical definition of Fij is equal to the heat transfer from I to J divided by the surface area of I times the radiosity from I. So just remember these 2 points. This is important because this tells us what kind of surfaces we can use this view factor thing on. We're not learning about what to do with non-diffuse radiation, but it's important to know the limitations of what we're applying. Okay? If we're trying to figure out the radiated energy off of a mirror, it doesn't work because mirrors don't. Right? Mirrors wouldn't work very well as mirrors if they scattered light back uniformly. Okay, you wouldn't be able to see yourself. It would just be an indistinct lit up surface. And then this is important because we want to remember that the amount of energy radiating away from a body isn't just what it's actively emitting, it's also what it's bouncing off from its surroundings. So, all right, so we learned about the 4 rules for view factors that are useful for computing, figuring out what view factors are if we're given at least one of them to start with, right? The other, so if we don't know one of those view factors to start with, the question is, how do we get it? Right? This is the real practical question. Fine, in an enclosure, I'm given f11, f12. So find f13, but how do we figure out what f12 is? In the most general sense, we're never actually going to compute this integral, but the view factor Fij can be computed as over ai times integral over ai to aj theta I cosine theta j pi r squared Okay, so if like I said, we're not gonna evaluate this, but if you kind of looked at this, you might notice that it's familiar in that what's inside of the integral here looks a lot like what showed up when we were figuring out the amount of radiation that left one surface and hit another one in the example we did in the middle of last week from 2 flat surfaces. We ended up with these cosines of the visible ray from one to the other with respect to each of their surface normals, etc., etc. And in the end, we said, well, we can solve it more easily using this idea of a view factor. We haven't actually gotten around that step of evaluating this integral. It's just that somebody's already done it for us. So instead of evaluating this integral, as I just said, what we're typically going to do is look at tables 13.1, 13.2, and in some cases 13.3 in the textbook. So view factors for common configurations, for our common geometries, have been computed already and are located in table 13.1, 13.2, 13.3, as well as figures 13.4, 13.5, and 13.6. So we're going to see how we use these in a quick example here. Let's say we've got a truncated cone, okay? And we're interested again in what's going on the inside of this truncated cone. We know that the large radius here, R2, is equal to 0.6 meters. The thing has a length of 1 meter, okay, along its axis. And the small end here has a radius R1 of 0.25 meters. So if we're asked to find F1, I forgot to mention, and so surface 1 is here, surface 2 is here, and surface 3 is actually going to be this lateral surface of the cone. So we're asked to find F13. That is the amount of energy that's radiated from this small cap on the cone into the cavity and hits right? This lateral surface. So to solve this one, what we would do is we'd open the book and we'd look at specifically, we might peruse through table 13.1 and realize that table 13.1, I should open this up, .cam. Okay, so we might look at 13.1 and realize that 13.1 deals with two-dimensional geometries. So that's not the one we want because we have had a three-dimensional geometry here. About table 13.2, you see three-dimensional geometries. Okay, so this is going to require some more of these logic steps, right? We've basically got radiation between two square surfaces, two circular surfaces, or rectangular surfaces that are at right angles to one another. Those are the three-dimensional geometries we have to work with. We're actually going to go with this guy right here, and here's the logic. If we can figure out the view factor from the small cap to the large cap, okay, the summation rule tells us that the view factor from this to this must be 1 minus the view factor to any other surfaces in this enclosure, right? So we're basically going to figure out the view factor from the small cap to the large cap and subtract that from 1 to figure out what the view factor is to the lateral surfaces. Because again, the radiation from 1 has to hit something. So what doesn't hit the large cap at the end will hit the sides of the cone, is the logic. So we've got an equation here, or we can, if it says right here, figure 13.5. What that is basically it is this equation in graphical form, which is actually a bit easier to work with. And so we would find that in figure 13.5 here. And I've actually got that loaded up on the slide here so we can draw on it. So the two factors we need to figure out, right? If this is our definition, the problem definition, we said that the I guess we're looking for Fij, so our small cap is going to be the one that's shown at the bottom here. So we had that Ri was equal to 0.25 meters, that Rj was equal to 0.6 meters, and L was equal to 1 meter. Okay. So L over R1, that's what's on the x-axis here. So L over R1, 1 meter over 0.25 meters. So we're looking for something along this x equals 4 line. Let's draw a solid line. Okay. And then these curves represent different values of R2 or Rj, okay, over L. So 0.6 over 1. So we're looking for the 0.6, which is this curve right here. And so we're going to get this intersection right about this point, okay, which gives us a view factor of approximately, it's right around here. I'd say this is around 0.26, roughly. Any questions here? Okay, so that gives us F12. Okay. So if we come back here, right, we know that F12 is equal to 0.26, and this is from figure 13.5. Then we would apply the summation rule, which says that F11 plus F12 plus F13 is equal to, equal to 1. Again, surface 1 is flat. Okay, it's not concave, so that goes to 0. We know that this is 0.26, and so we can solve for f(1,3) as being equal to 0.74. And we're done. Okay, let's flex this new approach a little bit more. What if I asked for instead how would we find f(3,3)? Anyone think that it's as easy as f(3,3) equals 0? Good. Because surface 3 there, right, it can see itself. It's concave. Some point on the lateral surface on the inside of this cone can see the other side of that cone. And so if there's a line of sight, then there's going to be radiation transfer. So f(3,3) will, well, the first thing we know is that f(3,3) will absolutely not be equal to 0. Okay. Because surface can see itself. All right, so how might we find f(3,3)? We're not going to try to actually come up with a number. Well, we may as well, but kind of in broad steps. What would be step number 1 if you were to puzzle this out? Which view factor would you try to find first? Let me ask it that way. Right, we've got f(1,1), f(1,2), f(1,3), f(2,1), f(2,2), f(2,3), f(3,1), f(3,2), f(3,3). Right. We know 3 of those at this point. Which other ones might we look for in order to find f(3,3)? f(3,1). Okay. That's the one we're going to need, yes. f(3,1). And how would we find f(3,1)? What rule would we invoke? I heard a murmur. Reciprocity, right? f(1,3), we've got it. If we flip those indices, f(3,1), then that means we're trying to use the reciprocity rule. Reciprocity, reciprocal. If we know f(1,3), we know the surface areas, we can get f(3,1). So f(3,1) by reciprocity, which would say that f(3,1) is equal to there we go. f(1,3) times A1 over A3. Okay, we don't know A1 and A3, but we've got the dimensions of the thing, and a quick search on Google will reveal the equations that you use to find the surface area of the lateral surface of this cone. Okay, so I'll go ahead and write these down real quickly. Right, A1 would be, of course, pi r1 squared, which is 0.196 meters squared. A2 would be pi r2 squared, which works out to 1.13 meters squared. And A3 is a little bit messier, but you end up with pi times r1 plus r2 times square root of R1 minus R2 squared plus L squared. And this is 2.83 meters squared. So we've got our three surface areas. Go ahead and assume that we know those. So if we know A1 and A3, we've got F13 right here. We can find F31 pretty trivially. Should be right, 0.74 times 0.196 over 2.83, in both cases meters squared, and this should work out to a value of 0.052. Okay, so we've got F31. We want F33. Which one would we? What's the missing link? If we want to use the summation rule, we need F32. Okay, F32 is a little bit more involved to find, so we have to figure out now how to trace backwards, find F32. So there we go. So we need F32. Again, the idea here is if we wanted to mirror the process, right? So F32, ideally, we would get by the reciprocity relationship from F23. And F23, we could find pretty much the same way we found F13, right? Just make some sense. So F32 by reciprocity, which says that F32 is equal to F23 over A3, which means we need to find F23. F23 we could go ahead and get by the summation rule. Basically saying that F23 plus F21 is equal to 1. Okay. Which means we need to figure out what F21 is. F21 by either, we have two ways of doing this. We could either use reciprocity with F12, or we could go back to the table or that figure, this guy right here, and we could just flip I and J and look up a different value on the graph. They're going to give us the same answer. Okay, we'll go ahead and go with reciprocity because it's most consistent with using these rules. F21 by reciprocity, which says that F21 is equal to A1 F12 over A2. Okay, so we've got a line on how to do this now. In other words, let's go ahead and we can work backwards, right, up these values. So F21, if we went and plugged these in, we know F12, we know A1, we know A2. We would find that F21 is 0.043. Okay. F23. One minus F21, right? Which should indicate that this is equal to 0.957. So we've got F23. We'll plug that in to find F32. F32, here we go. 0.382. So we've got F32. We've got F31, which we calculated earlier. So these guys plus whatever F33 is have to equal 1. So by summation, F33 summation would say that F33 is equal to 1 minus F13 minus 31 minus F32, which would work out to 0.566. So, a little bit of bouncing around logically. Admittedly, not the prettiest formatting in terms of a solution, but are there questions on this process? Yeah.
Is there a way to do like a sanity check while you're going through this to make sure that your numbers are like reasonable? Like obviously F12 is like really small compared to, or F21 is like really small compared to F23. And, like,
Yeah.
related. Is there like a reason why it's so big?
Well, so you can kind of look at it just sort of first. The first thing I would do is just sort of look at the problem. Okay, like if we were to picture this particular thing as like maybe like a flashlight. If you were to put a flashlight at the end of 2, like how much light is going to find its way out of 1? It's going to be a very small amount. Like most of it's going to be incident on surface 3. Okay, so that's the first sanity check. You'd expect that like the percentage of radiation from a big surface to that small surface is going to be smaller than the percentage of radiation from that small surface to the big surface. The other thing you can do is along the way you can use these rules to check your values. If you know, for example, we find, well, I guess we use those rules to figure this stuff out, so that doesn't really work that well. Well, for this one in particular, since this is, well, we've got F21 says, this is the one where it's sort of, it's strange that it's so much smaller. The other way you could do it is, like I said, you could just do it a second way. So in this case, if we flipped, like I said, if we flipped I and J, and we said that R sub J was 0.25 and R sub I was 0.6, then instead of, we'd be basically looking up 1 meter over 0.6, which would be around 1.6-ish, which would land us right around here, right? And then 0.25 over 1 should get us 0.25, which would be somewhere kind of, it would be a curve somewhere right around here. And so it's the idea is like we can see that it's less than, it's right around 0.05. And so there's another kind of sanity check that you're not totally off base. But in general, if you're computing multiple view factors, the best things to check are that if you're finding all the view factors from one surface, make sure they all add up to 1. And then if you're finding view factors multiple ways, or like multiple view factors using graphs like this, you can use the reciprocity rule to make sure that they agree with each other. Okay, so that really, actually, we're kind of at a position now where we should. The last thing I wanted to talk about in this class, right, was like using. So this is the idea of view factors. Now we can find the amount of energy radiated from one body to another, as long as we know the view factor and the total radiosity of that body. So if we've got some surface here, we'll call this surface 1. Got another surface here. We'll call this surface 2. We generally say that what's in the middle here is what's called a non-participating medium. That means basically it's a vacuum, or it's something that doesn't substantially alter the propagation of radiated energy. Right. If we did a surface energy balance on surface 1, we could find the net heat rate from surface 1, which is defined as, right, positive out. This would be A1 times J1 minus A1 times G1. All right. The radiosity, everything that's radiating out, times the surface area, minus the irradiation, everything that's coming in, times the surface area. And what we would find is, we're going to sort of fast forward through this part. We might need to wrap it up at the beginning of Wednesday. Is that basically this G here gives us some trouble unless we make some assumptions. Those assumptions are that the surfaces are together form an enclosure, meaning that somewhere they connect together. Okay. If they form an enclosure, then the beauty is we can apply things like the summation rule. The other assumption we can make is that they are diffuse gray surfaces. And at the yeah, we're going to have to wrap this up on Wednesday morning. What I wanted to do was discuss where to find the results for heat transfer between two surface enclosures. That is, when you only have two surfaces that somehow connect together or else extend infinitely on. So for the last problem on the homework, right, this is where this comes into play. The idea is you have two plates of glass separated by a small gap. And that's what's known generally as a two-surface enclosure. Those two plates of glass don't touch each other. That's true. The idea is that they are so close to parallel, or that they're relatively large compared to the gap between them, so that you're pretty justified in saying that 100% of the energy that's radiated from one hits the other one. Okay. And in other words, like any energy that leaves surface 1 has to hit surface 2. And all of the energy into surface 2 has to come from surface 1. And in that, under those assumptions, and like I said, we'll wrap this up first thing on Wednesday. But this is where you can find the stuff to help you out on that last homework problem. So there's this thing called the two-surface enclosure. Like I said, let's zoom out. The two-surface enclosure. And this is right here. The foundational relationship for a two-surface enclosure is that all of the heat out of one has to hit two, and that transfer from 1 to 2 accounts for all of the radiation energy exchange. And then if you come over to this table here, if you have large, approaching infinite parallel plates or planes that each have a temperature, an area, and an emissivity. Let's zoom in a little bit on that. Right? It makes sense that these two surface areas, you would say, are equal to one another. That the view factor from 1 to 2 would have to be 1, and that the view factor from 2 to 1, then, by reciprocity, would also have to be 1. And under those assumptions, you can figure out the heat transfer from 1 to 2 very simply using this equation. So this is going to be the key to solving that last problem on the homework. And so we'll fill it. We'll flesh this out a little bit on Wednesday, but I want to make sure you know where to find the equations you need. All right, we'll reconvene on Wednesday, wrap this up, and then I'll spend the rest of Wednesday and Friday doing examples and worked examples.